All right, in the next part, we're going to talk about more in-depth regulation of glucose metabolism, and we're going to focus on insulin and glucagon. And this all has to do with maintaining a good level of blood sugar, okay, concentration of glucose in our blood. So it is very, very critical that we have a readily available supply of glucose in the blood. But we don't want too much and we don't want too little, all right? So think about all the things that your body's constantly undergoing, whether you're exercising, eating, sleeping, taking medication, you're under stress. All these things affect your blood, your body, and things like your glucose levels, okay, if you're eating a meal. And so the body has to work very hard to maintain a normal concentration of blood glucose, which is between 65 to 100 milligrams of glucose per deciliter of blood. All right, and that is normal concentration range. So anything below that, low, would be considered low blood glucose levels. This is known as hypoglycemia. And anything above that would be high blood glucose levels, known as hyperglycemia. All right, so we have hormones and enzymes that help us regulate this. So the hormone that you see below is insulin, and insulin is created as a zymogen. So it's created in an inactive form. You can see that there's two peptide chains, and they're held together by these disulfide bonds between your cysteine amino acids. And so it's created as a zymogen, it's asleep, and then it is cleaved at both the amino terminal, the N terminal, and the carboxy terminal to become the active, awake form of insulin. And insulin is the responder when we need to lower, okay, so insulin responds when we need to lower blood glucose concentration. So I'm going to zoom in on this figure over here. Insulin is stored right here in your pancreas, in pancreatic cells. And when we need it, it is cleaved into its active form and it is dumped out. And what it causes us to do is insulin, I'm going to use these red arrows to say it's going to pull glucose out of the blood. So you see how these red arrows are going opposite of the purple arrows? Well, this one's not, but insulin is going to pull glucose out of the blood. Okay, glucagon, which I'll do in purple, is going to do the opposite of that. Glucagon is going to do some things that's going to ultimately dump glucose back into the blood when we need to raise our concentration of glucose in the blood. Okay, so you can see that we're about to talk a little bit about glycogen and glucose. So glucose is stored in the form of glycogen in the liver, and then glycogen is converted back into glucose when needed so that it can be dumped back into the bloodstream. So you see a picture of a blood vessel down here. But by the way, with these little yellow dots, you probably, these would be little dots of glucose, okay, in the blood or being pulled out of the blood into the liver. All right, let's look at exactly what insulin and glucagon do. There's 4 major things that each of these do, and some of them are just going to sound like exact opposites. So when we need to raise when we have rising blood glucose concentration, like our blood glucose is increasing and we need to maybe maintain it or pull it back down or decrease it, this is when insulin responds, okay? So insulin lowers blood glucose under the condition that our blood glucose is rising and potentially rising too high. And what's it going to do? It's going to cause glucose to enter the cells faster. So if it's being pulled out of the blood and being pushed into cells, then it's going to lower our blood glucose concentration. It's also going to cause glycolysis to speed up. So if we are breaking down glucose, then we are decreasing the concentration of glucose available in our blood. So it's going to speed up glycolysis. And then it's also going to increase glycogen synthesis. Okay, so it's going to make more, or instead of make more, I think a better way to say this is convert glucose into glycogen. Okay, so it's going to pull glucose out of the blood, take it into the liver, store it as glycogen. That's going to decrease your blood glucose concentration. And then it's going to, if we have any glucose left over and we don't know what to do with it, it will use it to synthesize amino acids and lipids. Oop. Okay, so it'll just take any extra glucose and use it to synthesize these non-carbohydrate biological molecules. All right, so those are the things insulin does. So glucagon is the opposite of that. When we have a falling blood glucose concentration, so our blood glucose is becoming too low, now glucagon is going to respond. And it's going to do some opposite things. It's first going to cause an entry of glucose in the cells to slow down. So it slows the entry of glucose. Whoops. Into cells. That way it stays in our blood longer or better. It's also going to cause glycogen to break down. Breakdown of glycogen. So again, glycogen is stored in the liver, and if we break it down into glucose, then we can dump it into the blood, which would increase our blood glucose concentration, which is what we want here. And then it's also going to cause the breakdown of lipids and proteins into glucose. This happens via gluconeogenesis, which is honestly the last one. Gluconeogenesis accelerates. Say speeds up. Okay. So know these functions of insulin and glucagon and how these two things regulate your blood glucose concentration. We also need to talk about what happens to the metabolism of glucose under stress or during stress when we're in a state of starvation, dieting, fasting. How does our body handle glucose and maintaining blood glucose concentrations during these times? So when you're in a state of starvation, dieting, or fasting, glycogen is going to break down into glucose. Okay, you are not getting glucose from your diet because you're either not eating or you're dieting on carbs, and so you are starving for glucose, your body is, and so we're going to use any reserves we have. We're going to break them down. So remember, glycogen is stored in the liver and in your muscle cells. The caveat here is that glucose plus glycogen, the readily available amount of glucose in the body, and any glycogen we have, which is the stored form of glucose, this represents less than 1% of our energy reserves. So we're really in trouble if we are in this state for a long time. All right, so when we use up those reserves, what else are we going to do? We are going to start to break down fatty acids. Okay, so fatty acid metabolism will kick in. Our fats, which by the way are our largest energy reserve, they will be metabolized to acetyl-CoA, which remember can then be used to run the Krebs cycle, produce reduced coenzymes, run electron transport, and give us the ATP that we need that we're not getting from glycolysis. All right. Now, the caveat here is that it takes a few days, okay, to fully transition from glycolysis over to fatty acid metabolism, okay, to kind of switch the fuel source of your body. And so that would happen eventually, but to get there, it's going to take some time. We can also metabolize protein into amino acids because remember, I have to scroll back all the way up to the top, but we can use non-carbohydrate sources such as lactate, amino acids, glycerol to make glucose via gluconeogenesis. So we can use other types of biological molecules to make glucose if we're not getting it from our diet. And then eventually the production of ketone bodies from acetyl-CoA. So if we are just making a lot of extra acetyl-CoA, which happens from fatty acid metabolism, we end up with too much acetyl-CoA. Acetyl-CoA will be metabolized into ketone bodies, all right? And again, this is what happens on the keto diet. And those will be used, these ketone bodies will be used for ATP synthesis to some degree as well. And these are the different ketone bodies that are a byproduct of fatty acid metabolism. You don't have to memorize the structure of these, but you probably recognize there's a ketone group here and here. This other one actually doesn't have it's a carboxylic acid, but it's classified in this group as well. It's a byproduct as well. So I think that's going to be the end of this section, and then we're going to pick up with glycogen metabolism for the last section.